Uh-oh. Does anybody else smell smoke? Hi, I'm Kevin. Welcome to my cave. Last time, we started exploring transconductance amplifiers, which take a voltage as an input and produce a proportional current as an output. The first ones we looked at had floating sources and loads, meaning they were not referenced to nor returned to ground. We learned how to use a couple of op-amps and transistors to build a voltage-controlled current source that didn't have that problem, and tamed several of its misbehaviors at the bench. I promised that this time we'd upgrade this device to handle a couple of orders of magnitude more current. Let's get started. Our output stage looks like this at the moment, with a little MOSFET and a fairly sizable sense resistor. The 100 ohm sense resistor will give us 10 milliamps for every volt of input signal. We could upgrade that to an amp per volt by replacing the 100 ohm resistor with a 1 ohm one, but running over an amp and dropping most of that 15 volts through that little MOSFET is going to melt it. I could replace it with a beefy power MOSFET, and in a production design I probably would, but I don't have one on hand at the moment. Also, power MOSFETs have a lot of gate capacitance, which is hard to drive stably. I'm not sure that this feedback filter would be enough to keep the circuit from oscillating. I'd have to be cleverer, and I don't really want the hassle. Instead, I'm going to recruit an NPN power transistor to help out. I'll include a little resistor to provide it with base voltage. This circuit is a cyclide pair, which you may have seen over in the Transistors 101 series. Instead of a BJT, it's using a MOSFET for the input, but the ideas are mostly the same. Let's go over how it manages its currents. Before we continue, let me interrupt for just a moment. Longtime viewers of this channel will know that it's always free to all comers. Nothing is ever paywalled. But I do end each video asking one thing, that you take care of one another. To that end, all the advertising revenue that I earn from this channel goes to charity. The current featured charity is called Heifer International. Heifer's mission is to end hunger and poverty in partnership with the communities it serves. It begins with a seed investment in livestock or agriculture, together with mentorship to help its participants build a business. The participants, small farmers, ranchers, and female business owners, are able to learn a living income and continuously lift up their communities as they train the next generation of leaders. I'd like to ask you to join me in supporting this organization. I set a goal of $500, which is enough to give a cow to a family in need, together with training and education in how to care for her and how to access the market for her milk. I know that with the generosity of Kevin's Cave people, we'll just crush that goal. Won't you help out today? There's a link to donate, up here, or down there, or at any rate somewhere nearby. Thanks so much, and now back to the video. I think it will be easiest to explain if we watch a circuit simulation. I've chosen component values for an output current of up to 1.25 amps, and I want to use a 15-volt supply. And I want to make everything robust enough to drive the full output current into any load from a short circuit to 10 ohms. The Circuit.js model is on the project GitHub, link in the video description if you want to play along at home. I've added current indications to most of the wires so you can see what's happening. At the lowest current levels, the power transistor is cut off. The MOSFET is carrying all the current, and it's all flowing through the 33 ohm resistor between the base and emitter of the power transistor. A small current, up to about 15 or 20 milliamps, will develop a less than a diode drop across the resistor. And so the current in the big transistor is going to be negligible. This is just like our previous circuit. By the time we're up to about 20 milliamps, though, the base emitter voltage has climbed to at least a 600 millivolt diode drop. We start seeing a collector current of a couple of milliamps, and the power transistor is carrying 10% or so of the load. After that, as the output current increases, the power transistor carries almost all the increase. By the time we're up to 150 milliamps or so, the current in the MOSFETs increased to only 25 milliamps, so the power transistor is carrying 5/6 of the load. Let's change the scale some to take the current still higher. The increase in the current in the MOSFET stays modest. By the time we're all the way up to 1.25 amps, which is what I've designed for here, we're pulling only a little over 50 milliamps of the MOSFET. And this is making a really conservative assumption that the beta of the power transistor is about 40. If we assume a more typical beta of about 70, the current in the MOSFET drops to about 40 milliamps. But that's large enough that we have to think about heating in the MOSFET. At full rated current into a short circuit load, it'll be dropping about 13 volts and passing those 40 milliamps. That's a little over half a watt of power dissipation. BS250 is rated for 700 milliwatts, so that's not really comfortable. But I'm not too worried because I'm thinking of the short circuit load as a fault condition. We can always choose a bigger MOSFET if necessary. Or with careful calculation, we may be able to make this 33 ohm resistor bigger and get rid of some of the parasitic current down there. But still, that's just the first item of thermal management we have to think about. The sense resistor is another component we have to size appropriately. If we run a current of 1.25 amps through a 1 ohm resistor, it'll drop 1.25 volts and dissipate about 1.6 watts. A 1 watt resistor won't be enough. Even a 2 watt one will be marginal. Running a resistor at full rated power gets it hot enough to burn your finger, so I don't like to exceed half the rated power except for brief surges. I have some 1 ohm 3 watt resistors on hand, so I'll use one of those. Now we come to the hardest part, the power transistor. At full rated current delivered into a short circuit, it's dropping 14 volts. 14 volts times 1.25 amps is 17.5 watts. We definitely need to worry about thermal management. The goal here is to keep the temperature of the transistor junction within a safe limit. The datasheet will give information about what that limit is, but we'll soon see that all the numbers in the headline have to be taken with several grains of salt. To begin with, we should ignore the headline specs of 10 amps, 60 volts, and 75 watts. In any circuit except for a saturated switch, those numbers are meaningless. Instead, we need to look at the safe operating area of the transistor. I haven't yet covered transistor heat sinks in the channel in any amount of detail, so it's time to do that now. There are 4 limits that we absolutely have to observe. The first one, at upper left, is the current limit of the bond wires inside the transistor package. That's what's usually shown as the headline current figure in the datasheet. There's no problem here. I'm not planning to send anywhere near 10 amps through the thing. The one at extreme right is the breakdown voltage of the semiconductor junctions. That's usually shown as the headline voltage on the datasheet. Again, there's no problem. I'm not going to pull 60 volts from a 15-volt supply. The one at middle right is the so-called second breakdown limit. The junctions of a big power transistor have a fairly large area and are not perfectly homogeneous. When running at high voltage, they will develop hotspots that limit the current handling even before the overall thermal limit of the device is reached. This limit may be quite significant indeed, depending on what you're doing. We'll keep this one in mind. Finally, we come to the thermal limit, the maximum power that the device can dissipate. Even in the graph on the datasheet, this line is an utter fairy tale.
The reason is that it assumes a case temperature of 25 Celsius. In a circuit that biases the transistor into the active region, I suppose you could get that with water cooling, maybe. But anyone who's worked with active power transistors knows that they get hot in operation. Instead, we have to start with the device's limit of 150 Celsius for the junction temperature and do the thermal calculation.
But how do we do that? Well, for a simple case like a transistor on a heatsink, there's a simple analogy that works for calculation. Almost everyone in high school physics gets taught an analogy between water moving in pipes and electricity flowing in circuits. In that analogy, among other things, we think of voltage as analogous to water pressure, current to flow rate, and resistance to some nebulous concept of resistance in a constricted pipe. This analogy often makes me cringe. First, because the teachers push it far beyond the point where it makes sense, leaving the students with a lot to unlearn as they progress. And second, because the students don't really know anything more about hydraulics than they do about electronics. Be that as it may, let's introduce another bad analogy, the thermal circuit. We can analogize voltage to the temperature at a particular location, and current to the heat flow between locations measured in watts. We can introduce a concept of thermal resistance, measured in Kelvin per watt, which describes how much the temperature rises or falls along a given path in proportion to the heat flow along it. The point of this analogy is that we can calculate using the analog of Ohm's law. The temperature difference across a path is the product of the heat flow along it and the thermal resistance along it. What I'm about to say will give heat transfer experts the screaming horrors. But for a simple case like two transistors mounted on the same heatsink, you can generally get away with also assuming that Kirchhoff's laws hold. Otherwise, you'd need to trot out all the head-splitting stuff that you learn in a course that in my undergraduate days was often called thermogoddamits. We'll start our thermal circuit with our transistor, more precisely, the PN junctions. The junctions are a heat source, dissipating about 17.5 watts. And we have to hold them below 150 Celsius. The heat source is analogous to a current source. The first place that the heat has to get to is the contact area on the back of the transistor case. The transistor manufacturer has told us the thermal resistance between the junction and the case, 1.67 Kelvin per watt. We'll write that down. Next, the heat has to transfer from the case to the heatsink. That heat flow might have to run through a film of grease, or a mica insulator, or what I'm using, a sheet of thermally conductive silicone. Unfortunately, the datasheet for the insulator that I'm using doesn't give the thermal resistance as a simple number. Instead, it tells me that the sheet is 0.15 millimeter thick, and gives a value for the thermal conductivity of the material that it's made of. I had to go elsewhere on the net to find a mechanical drawing of a TO220 transistor, and from that get the area of the contact surface. From all that, I can compute the thermal resistance through the pad. Since the pad was sized specifically for a TO220 device, would it have killed the manufacturer to print this number somewhere? Now we can move on to the heat transfer between the heatsink and the ambient air. The datasheet for the heatsink gives a bunch of values for the thermal resistance, depending on airflow. I look at the one for natural convection, and I'm virtually certain that won't work. So I'll use the value for an airflow of 200 linear feet per minute, blow my desk fan over the breadboard, and make a note that if I build this as a permanent fixture on the bench, I need to use a better heatsink. I'll pencil in that 5 Kelvin per watt number. Since we're assuming that both Ohm's and Kirchhoff's laws have analogies in this sort of thermal circuit, thermal resistances in series add. That gives us a total thermal resistance of 8.3 Kelvin per watt. And we can calculate how much power we can dissipate without pushing the junction past 150 Celsius. I get a figure of 15.1 watts. If we take the safe operating area graph and plot the load line for 15.1 watts, you can see why I say that the graph is a fairy tale. You never have the case temperature that low. But now let's see where our actual numbers land. Under full amp and a quarter current and a short-circuited output, the transistor will drop 13 3/4 volts and dissipate 17.2 watts. That's outside our safe operating area. Oops, what can we do about that? Well, we could negotiate specifications. One possibility would be to use a 12-volt supply instead of 15 volts. That would mean that the transistor would drop only 10 3/4 volts under full rated current. That's within the safe operating area. The drawback is that the circuit would saturate under a load of a little over 8 ohms rather than the 10 that we wanted. Or we could require that the load be at least 1.8 ohms. With that much load, the transistor is dropping 11.5 volts, again inside the safe operating area. But we'd have to design some other kind of short-circuit protection to avoid blowing things up if the output is inadvertently shorted. Or we could settle on a 1 amp current limit instead of 1.25 amps. With a 15-volt supply, the transistor will drop 14 volts with the output shorted, and 1 amp is within the safe operating area. But by far the best option is simply to use a better heatsink than the stamped metal one I found in my parts box. A check with my distributor turned up one from Boyd that's a little over $3 in unit quantities, and has a graph like this. It's a little hard to read, but the ascending lines are the ones for natural convection, that is, no fan, and read out on the left and bottom axes. At the 17.5 watts dissipation that we calculated, the graph shows a temperature rise of 56 Kelvin. Does that work for us? Well, let's take that 56 Kelvin figure and transfer it to our heat transfer schematic. Assuming that the ambient temperature is 25 degrees Celsius, that will give us a temperature of 81 degrees Celsius at the base of the pad. The temperature rise across the pad will be 1.63 Kelvin per watt times 17.5 watts, or 28.5 Kelvin, giving a temperature of 109.5 Celsius at the contact surface of the transistor case. And the rise between the case and junction will be 1.67 Kelvin per watt times 17.5 watts, or 29.2 Kelvin, for a temperature of 138.7 Celsius at the junction, which is pretty toasty, but less than 150, so we should be safe if somebody short-circuits the output. Now you see why linear power circuits have such massive heat sinks. They're ridiculously inefficient, but they're electrically quiet, which is sometimes what you need. For now, I'll run the demo with a 3.3 ohm load, 3 10-ohm 5-watt resistors in parallel, and use the heatsink I have with the fan blowing on it. That should keep things cool well enough to show off the circuit. By the way, this MOSFET BJT combination is available as a single integrated device called an IGBT, insulated gate bipolar transistor. Those are the real rock crushers in the transistor world. Some of the ones on the market can withstand up to a few kilovolts and switch 1,000 amperes or so. But back to our amp and a quarter circuit. I went and built it out on the breadboard. But when I tried it, it started oscillating. Again. And this time, I lost the footage, and when I tried to reshoot the scene, it obstinately refused to misbehave. Sometimes video production is like that. Anyway, let me explain what I think happened. We started with a circuit like this. I've replaced the Cycli pair and base to emitter resistor with the schematic symbol for an IGBT for clarity. The mistake that I made was to connect the sense resistor to the breadboard's plus 15 volt line and return the load to the breadboard's ground. With an amp and a quarter flowing, there's a problem with that. The wiring resistance, tiny as it is, becomes too great to ignore. There's some resistance throughout the breadboard, making its power rails into tiny voltage dividers. Whenever the output current changed, the voltage that propagated through the power and ground lines was enough to upset the delicate balance of the control circuit,
and made the op-amp see positive feedback at some high frequency. The solution is to connect the sense resistor to the power supply via its own wire, and similarly to return the load to the power supply's ground via a dedicated wire. That way, the heavy current won't run through the breadboard's power bus and disrupt the control circuit. I was also worried that sudden changes in current might upset the reference voltage, so instead of deriving it from a voltage divider connected directly to the power supply, I derived a stable 2.5 volt level using a TLV431 bandgap reference, and adjusted the resistors to divide that level down to the 0 to 1.25 range that we need. I also added a capacitor to filter out whatever residual junk might be coming through the power leads from the neighbors on the breadboard, and I was ready to try to film again. I've made all these changes, and this breadboard layout is the result. The finer gauge red and white wires from the power supply are powering the sensitive analog control circuitry. The high current path, including the power transistor, the sense resistor, the MOSFET, and the load, gets its power from a separate dedicated wire coming directly from the power supply. The load current runs through the ammeter and returns to the power supply, again through a dedicated wire. I've added the circuit with the voltage reference down here. So let's ramp up the current and see how it does. The output is tracking the input, although it's about 3% low. That doesn't surprise me terribly. I'm accumulating a bunch of component tolerances. I could fix that by trimming one of the 10K resistors in the middle. What about the thermal issues I've been so worried about?
I'll use a literal rule of thumb for finding a heatsink temperature. Wet your thumb and touch it quickly.
If it doesn't sizzle, the circuit is probably not frying itself, and you could probably try a slightly longer finger touch. Ouch! That heatsink is hot! If I jerk my hand back within seconds of touching it, that's probably about 60 degrees Celsius. The sense resistor is about the same. The MOSFET isn't quite as bad. Of course, it's more accurate to use a thermal camera. So here I've powered the circuit on, and I'm watching the temperatures go up. The sense resistor heats up first and settles somewhere around 60 Celsius. The transistor and heatsink warm up more slowly, but eventually also come up to a little over 60 Celsius. The MOSFET and the load resistors are only warm, about 35 Celsius for the MOSFET and 45 for the load. This is pretty much in line with what we calculated. I also tried running without the fan, and airflow matters. After less than a minute, the temperature of the heatsink reached the boiling point of water, and everything started to smell overheated, so I quickly stopped the test. Even the DuPont wires connecting the power transistor were starting to heat up. If their resistance is that significant, they could be part of that 3% error in the current that I noticed.
If we build things somewhat more robustly, which mostly means a bigger heatsink for the transistor, but maybe also a higher wattage sense resistor, this circuit could be a very quiet current source for the bench. I don't happen to need such a thing at the moment, so I'll probably just keep it in my notebook in case I decide to build it down the road. The big remaining drawback to this circuit is that when we went to a ground reference source and a ground returned load, we made the circuit single-ended. It can only source current, not sink it. Next time, I want to explore another transconductance circuit that can work in both directions. I hope you'll stay tuned for that, and maybe tell the YouTube algorithm that you want to hear when it comes out. In the meantime, stay safe, stay healthy, stay curious, and please take care of one another. Bye!